given a set of functional dependencies, we can compute all the keys of a relation. Now we are looking at the relation R with a set of attributes A, and we have the functional dependencies for the relation R. Then a set of attributes alpha is a key of the relation R if and only if the cover of alpha is equal to the set of all attributes of R. So the cover of alpha, remember that's all the attributes uniquely determined by alpha. So if alpha uniquely determines all the attributes of R, then this is a key. So this means that given a set of functional dependencies, we can use the functional dependency to determine all the keys. Usually we are only interested in minimal keys. We only want to have those keys where every attribute is vital. So if we remove an attribute from the key and then compute the cover, we no longer get the set of all the attributes. Finding some minimal key is really easy. Let's say we have a relation R with attributes A and we have a set F of functional dependencies for R. And now we want to find some minimal key for R. We start with a set of all attributes for R. So X is the set of all attributes. And then we check whether we can remove an attribute from X such that this attribute that we remove is still in the cover of X. So this means that we didn't need this attribute because it anyway is in the cover. And if so, then we can remove the attribute A from X, and we repeat this step until nothing can be removed anymore. And when nothing can be removed anymore, then X is a minimal key of the relation R. This will give us some minimal key, but depending on the order in which we remove the attributes, we might get different minimal keys. If you're just interested in some minimal key, then this is a very simple algorithm to find one minimal key. We will see on the next slide an algorithm for determining all minimal keys. As an example, let's consider this results table with the attributes sit, exercise, points and max points. And we have the functional dependencies. The sit and the exercise together uniquely determine points, and the exercise uniquely determines the max points. So now we want to find a minimal key for the results table. We start with the set of all attributes of this table. So X is the set of the attributes sit, exercise, points and max points. Next, we will check what attributes we can remove from this set. Clearly, we can remove the attribute points because the points is uniquely determined by sit and exercise. Sit and exercise are still in the set X. So if we remove points, then points will still be in the cover. So we remove points and we have now the set sit, exercise and max points. Now we can remove max points because exercise is still in the set and exercise uniquely determines max points, so that when we remove max points and compute the cover, max points will still be in the cover. So now we have the set X being equal to sit and exercise. Can we remove something from this set? If we remove exercise, then nothing is applicable anymore, so exercise is no longer in the cover. If we remove sit, then only this function dependency exercise is applicable, so then max points is in the cover, but sit is not in the cover. So we cannot remove anything anymore, so this is a minimal key for our relation R. The algorithm shown on this slide can be used to compute all minimal keys of a relation based on a set of functional dependencies. We are looking at a relation R that has attributes A1 up to AN, and we have a set F of functional dependencies for this relation R. And the output of this algorithm is the set of all minimal keys of the relation R. Initially, the set of results is empty. We will add things to the set during the computation. During the computation, we also keep a set of candidate keys. Initially, we put as a candidate the set of all attributes AI that do not appear in any right-hand side of a functional dependency. The attributes that do not appear in the right-hand side of functional dependencies, this means you can never get them via a cover, so they are not implied by any functional dependency, so they have to be part of the key. So this is the first step. You look for all of the attributes that are not in any right-hand side, and they need to be part of any key. Next, we are executing this while loop as long as we have a non-empty set of candidates. In each step, we pick a smallest candidate kappa from the set of candidates, and we remove it from the set of candidates. We check whether kappa already contains a key in the result set. So if kappa already contains some minimal key, then we don't need to continue. Then kappa itself cannot be a minimal key, so we can disregard it. If it does not contain a minimal key in the result set, then we check whether kappa is itself a key. We do so by computing the cover of kappa. If this cover is equal to the set of all attributes, then kappa is a key, and we add kappa to the results. If kappa is not a key, so in the else clause, then we extend this candidate kappa with certain attributes. With what attributes do we extend? We pick all the attributes AI that are not part of the cover of kappa. So those attributes that are on the cover, they anyway are implied by kappa, so we don't need to add them. So we look only at the attributes that are not in the cover, and then for each of them, we create a new candidate kappa I that is the extension of kappa with the attribute AI. And then we add this new candidate kappa I to the set of candidates. And then this whole procedure repeats. We again remove one smallest candidate from the set of candidates and so on. So let's see this algorithm on action in an example. So we are considering a relation R with attributes A, B, C, D, E, and we have the following set of functional dependencies. Now the first step is that we check what attributes do not appear in the right-hand side. The attribute A does not appear in the right-hand side. The attribute B does not appear on the right-hand side. C does, D does, and E does. So A and B do not appear on the right-hand side. So that will be our first candidate key. So we start with this set of candidates that contains the set AB. Next, we pick a smallest candidate. There's only one, so we'll pick this candidate. And we compute the cover. What's the cover of AB? From B we get C, we also get D, and from D we get E. So actually we get all of the attributes of R. So this means that the set AB is already key of R. So we already have found the only minimal key. There's no more candidates, so AB is the only minimal key of our relation R. So let's look at a slightly more complicated example. We again have a relation R with attributes A, B, C, D, E, and these are our functional dependencies. The first step is again to check what attributes do not appear in the right-hand side. The attribute A does not appear on the right-hand side, B does, C does, D does, and E does. So only A does not appear on the right-hand side, so we start with a set of candidates that contains only the candidate set of A. Next, we remove a smallest candidate. We have only one, and we compute the cover of this candidate. The cover of A is AE, So from A we get E and we don't get anything else. So the cover is just a set AE. This means we have to extend this candidate with all the attributes that are not in the cover. So we have to extend this candidate with B, C, and D. So we get 3 new candidates. We get AB, we get AC, and we get AD. Next, we can look at any smallest candidate. They all have the same size now. So we can, for example, look at AD. Computing the cover of AD gives us B also. So we get B. From B and D we get C, so we also get C. And from A we get E, so actually we get all of the attributes. So AD is already a key. So we have found one minimal key of this relation. Next, we have 2 candidates left. We have AB and AC left. So let's look at AB. We compute the cover of AB. What do we get? This is not applicable. This is not applicable. AE, this one is applicable. So this is the only applicable one. So we get, as a cover, we get ABE. So this means we have to extend this key with all the attributes that are not in the cover. So with C and with D. So we get ABC and we get ABD. ABC, ABD, and we still have the candidate consisting of AC that we didn't look at yet. As a next step, we again have to look at the smallest candidate. In this case, it's only AC. So we compute the cover of AC. The cover of AC will give us E again. This is not applicable, AD is not applicable, so indeed we get only ACE. This means we have to extend AC with B, so we get ACB, and with D, so we get ACD. So we arrive at this set of candidates. Now observe that 2 of these candidates contain a key that we have already found. Namely, ABD contains AD and ACD contains a key. So these we can throw away immediately because they can never give rise to a minimal key. They contain a key that's already in the results. So we throw away these 2 and are left only with 1 candidate, ABC. So we compute the cover of ABC. This gives us ABCE. So ABC is not a key. We have to extend it with the attribute D, but the extension with attribute D again gives us a set ABCD that contains a key that we've already found. So we don't need to consider this extension. So the only minimal key of this relation is AD. Let's practice the computation of minimal keys in the online system. Here we have a task that asks us to compute all minimal keys for a given set of functional dependencies. So let's get started. The first step is that we check for all the attributes that do not appear on the right hand side, and that will be our first candidate key. A appears on the right hand side, B appears on the right hand side, C appears, and D appears. So all of our attributes appear on the right hand side, so we are unlucky. We start with an empty set. Then we pick the smallest candidate, which in this case is the empty set. We compute the cover. What's the cover of the empty set? The cover of the empty set is just the empty set. So that means we need to extend this candidate with all the attributes that are not in the cover. All of them are not in the cover, so we need to extend the empty set with A, with B, with C, and with D. So these are now our candidate keys, A, B, C, and D. We pick a smallest candidate. So let's say we pick the set containing just A. We compute the cover. What's the cover of just A? this function dependency is not applicable, this is not applicable, none of them is applicable, so we just get A. We have to extend A with all the attributes that are not in the cover, so we have to extend A with, we get AB, we get AC, we get AD. Again, we pick a minimal candidate. Let's pick B. We compute the cover of B. What does this give us? We have, of course, in the cover B, we get C. Can we do anything else? The first not applicable, this not applicable, this not applicable. Okay, we get just B and C. So this means we have to extend this candidate with attributes A and D. A, B we already have, so we don't need to add this as a new candidate, but we need to add BD. Okay, we pick our next candidate, C. We compute the cover of C. We get C. What else do we get? Nothing is applicable, so we just get C. So we have to extend C with all of the attributes. CA we already have. CB we do not have yet. So we get BC. We get CD. Next we pick again the smallest candidate, D. Now we compute the cover of D. From D we get B. From B we get C. So we have DB, so we have B, C and D. What is now applicable? The first one is not applicable. B we have already, C we have already. From B and D we get A and C. So D already is a key. We get all of the candidates from D. So this is very nice. We have our first key. And this means that from this set of candidates we can now remove all supersets of D, all the sets that contain a key that is smaller. So AD cannot give, for example, AD cannot give rise to a minimal key anymore because D already is a minimal key. We can remove AD. BD also cannot give rise to a minimal key anymore because D is already a minimal key. And likewise, we don't need to consider CD anymore. Okay, so that has nicely reduced our set of candidates. We pick again a smallest candidate. Let's say we pick AB. We compute the cover of AB. What do we get? This is not applicable, this not. We get AB, we get C. And what else is applicable? From AB we also get D. So AB also is a key. So we have found the second minimal key, AB. Next, let's look at AC. What do we have? The cover, we get A, we get C. This is not applicable, this is not applicable. We don't have B, we don't have AB. So the cover of AC is just AC, meaning that we have to extend AC with all of the attributes that are not in the cover, so with B and with D. So in principle we have to add B and we also have to add D. However, we can immediately throw the extension with D away because this contains a minimal key, D. Likewise, we can throw ABC away because it contains the minimal key, AB. Okay. So we have only one candidate left, BC. We compute the cover. What do we get from BC? We get this not applicable, not applicable. C we have already. BD is not applicable, AB, so we just get BC. So we have to extend with A and D. So we get extension with A and we extend with D. The extension with D again contains the minimal key D, so we don't need to consider the extension with A contains a minimal key AB. so we also don't need to consider it. So we have found two minimal keys, D and AB. Let's check whether this is correct. Yes, our solution is correct.